Section 3.4, Substitution. Our objectives are 1. Find indefinite and definite integrals using substitution, and 2. Change the limits of integration. Integration by substitution. The method of integrating by substitution is related to the chain rule for differentiating functions. How the method of substitution works. Let's look at an example. Example 1. Consider the indefinite integral, the integral of 2 times the quantity 2x plus 4 to the 5th power dx. One way to solve this integral is to expand the expression and integrate the resulting integrand term by term. I don't know about you, but if I can find another way, I don't particularly want to expand this. An alternative approach simplifies the integral by making a change of variable. This is called U substitution. First, I want to take our original integral and I'm going to rewrite it just a little bit. Now, if I can simplify the inside here, that's going to give me something that I can integrate more efficiently. So what I'm going to do is let U equal the inside, 2x plus 4. Then du dx would be 2. In other words, du would be 2 dx. Now I have something I can substitute in directly. Here's my du, and here's my u. So my whole substitution would be u to the 5th du. And that is very straightforward to integrate. So 1/6 u to the 6th plus c. And now I substitute back in from the u. So 1/6 2x plus 4 to the 6th power plus c. And I'm done. The method of integration by substitution, the substitution method for antiderivatives, our goal is to rewrite the integrand as a composition of functions. So the integral of f of g of x, g prime of x dx, translate to the integral of f of u du. You need all the pieces to be able to integrate. First, you choose a u equal to g of x, where g of x is part of the integrand, usually the inside function of the composite function f of g of x. Since du dx is g prime of x, du is g prime dx. Then use the substitution u equals g of x and du equals g prime of x dx to convert the entire integral into one involving only u. Now integrate. If you don't have the right pieces, go back and try a different choice for u. Replace u with g of x at the end to obtain the final solution as a function of x. Let's do some examples. So the first thing I want to do is rewrite this function. I can see it makes sense that this would be the g of x. And I want to get everything else out of the way. So I'm going to rewrite this as x squared plus 3 to the 4th power 2x dx. Now if I let u be the inside here, x squared plus 3, then du would be 2x dx. And you can see I've got a perfect substitution here. So I can rewrite this whole thing as the integral u to the 4th du. Well, that would integrate very straightforwardly into 1/5 u to the 5th plus c. Now I'm going to substitute back in for u, so 1/5 times the quantity x squared plus 3 to the 5th power plus c. And we're done. Let's do another example. If we want to find the integral of e to the negative 3x dx, whenever you have e to some power, that's a good choice for u. So u is negative 3x, then du would be negative 3 dx. Now when I look here, I don't have a negative 3 anywhere in here, and I need to sub in for dx. So I'm going to take and divide both sides of this by negative 3. So du over negative 3 equals dx. Now I'll sub back in. So e to the negative 3x was u, e to the u, dx was du over negative 3, du over negative 3. But this is a constant, and we can always pull a constant out. So this is the same thing as e to the u times negative 1/3 du. So this is the same thing as negative 1/3 times the integral e to the u du. So that would be negative 1/3 e to the u plus c. Now sub back in for u, and we've got negative 1/3 e to the negative 3x plus c. And we're done. Example 4. Find the integral of x over 3x squared plus 1 dx. Now this looks like a good choice for u. The first thing I want to do is rewrite the integral as 1 over 3x squared plus 1 times x dx. So I'm separating this part out from everything else. Now if I let u equal 3x squared plus 1, then du equals 6x dx. Now, I don't have a 6 in here, I have an x dx, so I want to solve for the piece that I have left. So du over 6 is x dx. And now here, I'm ready to sub in. So this is the same thing as the integral of 1 over u du over 6. I'm going to pull my constant out, so 1/6 the integral of 1 over u du. Now I'm ready to integrate, so that would be 1/6 times the natural log of the absolute value of u plus c. Sub back in for u. U is 3x squared plus 1. So 1/6 natural log of the absolute value of 3x squared plus 1 plus c. Now it doesn't matter what x is. For this particular argument of the natural log, any x I put in here, once I square it, I'm going to get a positive number. Multiply it by 3 and add 1, I'm still going to have a positive number. So in this particular case, I could rewrite as 1/6 the natural log of 3x squared plus 1 plus c. The only time you can get rid of these absolute values is if there's no way that what's on the inside here, the argument, could be negative. Let's do another example. Find the integral of the quantity 5x to the fourth plus 5 to the 2/3 power 20x cubed dx. So we're going to let u be 5x to the fourth plus 5. Then du would be 20x cubed dx. Now that happens to be exactly what I have. So I can now translate into the integral of u to the 2/3 power du, and I have everything I need to integrate. So that would be 1 over 2/3 plus 1. That would be 5/3 u to the 5/3 power plus c, which is the same thing as 3/5 u to the 5/3 plus c. Sub back in for u. U was 5x to the fourth plus 5, so that would be 3/5 times the quantity 5x to the fourth plus 5 to the 5/3 power plus c. And we're done. Let's do another. Find the integral of ln x squared over 2x dx. Now again, I want to rewrite this a little bit. I want ln x to be my u. So I'm going to rewrite this as ln x quantity squared times 1 over 2x dx. So if I let u be the natural log of x, then du would be 1 over x dx. When I look here, I can see that this is the same thing as natural log of x squared times a half times 1 over x dx. So I can pull this 1/2 out. And now I'm perfectly set up for my substitution. Here's my du, here's my u, so that would be 1/2 the integral of u squared du. So that would be 1/2 times 1/3 u cubed plus c. So that would be 1/6 u cubed plus c. Sub in for the u. That would be 1/6 times the quantity ln x cubed plus c. Let's do some more examples. Substitution and the definite integrals. You have two possible strategies for using substitution to evaluate definite integrals. The original limits of integration were given in terms of x, not values of u. So 1, you can translate back to x's and use the original limits of integration, or 2, you could substitute the limits of integration. I'm going to demonstrate that. So we would be taking the definite integral from x equals a to x equals b of f of g of x, g prime of x dx, and translate it into the integral from u equals g of a to u equals g of b, f of u du. Let me show you how that works. Example 7. Evaluate the integral from 0 to 4 of x times the square root of 9 plus x squared dx. The first thing I'm going to do is rewrite this using exponential instead of radical notation And I'm going to regroup. I'm going to move this x over here. So this is the same thing as the integral from 0 to 4 of the quantity 9 plus x squared to the 1/2 power x dx. Now, if I let u be 9 plus x squared, then du would be 2x dx. But when I look over here, all I have is an x dx, and I need to sub in for that. So I'm going to divide both sides of this by 2, and that gives me du over 2 equals x dx. Now, I am ready to sub. Except, wait a minute, we're going to translate our limits of integration as well. Now, u is 9 plus x squared. So, if x equals 0, then u would be 9 plus 0 squared, or 9. If x equals 4, then u would be 9 plus 4 squared, so 25. So when I do my substitution, I now have the integral from 9 to 25 of u to the 1/2 du over 2. So I'm going to pull this 1/2 out. That would be 1/2 the integral from 9 to 25 u to the 1/2 du. So that would be 1/2 times 2/3 u to the 3/2 evaluated from 9 to 25. So that would be 1/3 u to the 3/2 evaluated from 9 to 25. So that would give us 1/3 times 25 to the 3/2 minus 9 to the 3/2. So that would give me 1/3 of 125 minus 27, so 1/3 of 98, so 98/3, and we're done. Let's do another example. Here again, the very first thing I want to do is separate my pieces out. So I'm going to rewrite this as the integral from 0 to 1 of 1 over x cubed plus 1 times x squared dx. And I'm going to let the denominator here be the u. So if u is x cubed plus 1, then du would be 3x squared dx. And I can see here I've got an x squared dx. So I'm going to divide both sides by 3. So du over 3 is x squared dx. And now I'm ready to sub. So here's my u, and here's my du over 3. But I want to translate the limits of integration first. So u is x cubed plus 1. So if x is 0, then u would be 0 cubed plus 1, or 1. And if x is 1, then u would be 1 cubed plus 1, or 2. So now I've got the integral from 1 to 2, 1 over u du over 3, pull that constant out, that would give me 1/3 the integral from 1 to 2 of 1 over u du, which of course we immediately recognize as keep the 1/3. This would be the natural log of u evaluated from 1 to 2. So 1/3 times the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. But the absolute value of 2 is 2, so the natural log of 2 minus the absolute value of 1 is 1, the natural log of 1. And now we're just going to put that in the calculator, and that would give us 1/3 times the natural log of 2 minus the natural log of 1. And there we are. So approximately and if you have homework problems with natural logs, make sure you look at how many decimal places they want you to go. So now you know how to do substitution. You know how to use it for definite and indefinite integrals, and evaluate from there.